You have one of them. 272,831.
I actually started my one to back us in more, so I wanted to worship.
I want to take the rules we already have and extend them into combination. I already know what to do if I'm adding or if I'm subtracting. If I'm multiplying by a constant. All of those rules came directly from our limit definition. But if I am multiplying two functions together, well, their product, that's x squared times x cubed, what do I get? And the derivative of x to the fifth, great. When I added, I just added the derivatives. When I subtracted, I just subtracted the derivatives. If I had a number and I multiplied, I just left the number there and took the derivative of the part. If I take f prime and g prime, what's the derivative of x squared? And the derivative of g, derivative of x cubed, that doesn't work. The derivative of f times the derivative of g does not give us the same thing as the derivative of the quantity f times g. What the? That, I don't like that. Okay. I am going to pull myself all the way back to Greek antiquity to talk about multiplication itself. When I think of multiplying in Greek terms, we almost always investigated numbers as physical lengths because all of Greek mathematics eventually became based on geometry, which means multiplication became length times length. Wait a minute, that's an area. So let's consider the image of a rectangle whose length is f of x and whose width is g of x. Well, then the area of this rectangle is fg. I want to know what happens to this when I change x, right? It's f of x plus h minus f of x over h. But if I change x in the area there, I have to change it in both the length and the width. So I can imagine a little change where this new length is f of x plus h, and this new width is g of x plus h. And what I really want to know is how did the area of my rectangle change? I should take the whole box, including the big blue stuff, minus just the box that has the brown stuff, and I should take the difference in those. I'm going to add two more little dotted lines here. Let's knock off that corner for a second, and let's look at these three different pieces. Because what I have here is a piece across the top, a piece across the right edge, and a piece in the corner. What is the length of this top rectangle? Which is the same as down here, right? But its width is really small, right? Its width is the difference between g of x plus h and g of x. Yes? What about this right-hand side? Not the corner, just the vertical strip. Its height is what? G of x. And its width is the difference in the f's, isn't it? Hey, wait a second. My goal is to figure out how much is in all three of those little bits, right? It's this upper corner that's the problem at the moment. That is going to be this thing times this thing, isn't it? Yikes. Okay. If I really, yes, sir.
What are those values? Value of that, both x to be the same.
Yes, the value of those x's is the same. The only difference is the h. So it's like we moved over just a little bit, like our secant line, right? We moved over just a little. But Zion, my eventual comment is that I'm going to let h go to 0, right? But I'm also going to do one other thing when I do a derivative. When I set up my limit definition derivative, I have to divide by h, don't I? Let's think about, do you want to look at the top strip or the right strip to start with? We'll look at the top strip to start with. But look at the top strip to start with. As h gets smaller and smaller and smaller, does this dimension, the horizontal dimension of that strip, change at all? It stays f of x. But the height gets smaller because h is getting smaller. If I were to take that expression, the area of that piece, as h went to 0, I'd have the limit as h went to 0 of all of this stuff multiplied together divided by h. Are there any h's in this part? If there are no h's, I can pull it out front, right? That means I'm taking the limit, as h goes to 0, of this thing divided by h. That's a derivative. That's not just any derivative, that's the derivative of g. So the f doesn't change, but g gets turned into its derivative. What's going to happen over here? Say it louder for me. So if I want this piece and this piece, I have one that stays the same and the other becomes the derivative, and then in the other strip it switches. What about the corner? Well, no matter what I do, both pieces have h's in them, right? That means the width and the height are both going to go to 0. So I'm going to get 0 over 0. But the top really has 2 zeros in it. The bottom line has 1. That's going to go to 0. The corner is basically going to become a dot. And a dot has no area at all. But that horizontal strip becomes a line segment. And that's got a dimension to it, doesn't it? The vertical strip gets squeezed down to be a line segment. And that's got a dimension to it. So these two pieces, they, quote unquote, they matter a lot more than this corner does. And so when I go to look at this change, what I end up with from this side is I end up with f prime, but g stays the same. When I look at this piece, I get f, but g changes. And that idea works. If I really want to be pedantic about it, I should go through the limit definition and do a whole crap ton of algebra and show you and prove, using an epsilon and a delta and all that fun stuff, that this is going to work every time. It ain't worth it. If I want the change in this area, what I should take is the derivative of these functions one at a time. The derivative of f, leaving g alone, add f times the derivative of g. But one at a time. Hey, wait a second. Let's check. Remember our example? F prime of x was 2x. G prime of x was 3x squared. And if I take f prime times g, I get 2x times x to the third. And if I take f times g prime, what do I get here? Zion, what about this one? And if I add those together, I get 5x to the fourth, which is, scroll all the way back up, what I wanted to get. So this mix and match, one from column A, one from column B, one at a time derivative, was originally written up by Gottfried Leibniz in Germany, and he wrote it in his differential notation. The derivative of fg is derivative of the first times the second plus derivative of the second times the first. And I always actually, instead of writing f and g, I usually write f and s for first and second. Now, I will admit, for the example we were doing, this is the long way to do it. It's easier just to multiply those two together, write down x to the fifth, and take the derivative that way. That's easier. So why would I do this crap? Because there are places where it's harder to simplify. Here's a function. There is no way, none, to combine the x squared piece with the e to the x piece. They have to stay segregated like this, separate from one another, which means if I want the derivative of this function, it's really two pieces that can't be combined. Have to use the product rule. What is the derivative of this function f? But wait, there's more. I told you I was going to use this phrase a lot. That's the derivative of the first, leaving the second alone. So now I need this part. It is. The f here doesn't change. Quite frequently, I actually leave them in order. I'll even write f and s. And so my derivative will be f prime s plus f s prime. Derivative of one at a time. Derivative of the first one, leave the second one alone. Leave the first one alone, derivative of the second. I can leave this just like this, or if you want, I can factor the e to the x out. I can even go a step further and factor out an x. All of this is optional. It's just going to depend on what reference you are looking this up in. In the back of our book, you'll actually see this version. Yes, sir. Well, I did really, right? But they're multiplied by two different things, aren't they? So I pulled the e to the x out and left the two different things. So I really did kind of add the coefficients together. More questions? Sometimes you have your choice. There are at least two different ways to do this problem. I could multiply out to start, or I could do the product rule. We're going to do them both. However, square roots give me the heebie-jeebies. I need to fix those to be able to take the derivatives. How do I rewrite the square root of x? A half power. So if I'm going to do the product rule, this is my first part. This is my second part. They were even nice to set it off in parentheses for me. I know that whole piece. So derivative of the first, power rule. Leave the second alone. Plus, now we leave the first alone and do the derivative of the second. What's the derivative of 1 plus x? That was easy. Now again, everything from here on down is optional. I'm going to simplify this so I can compare it to the version we're going to get when we do this the other way. So I'm going to multiply this through. And I get 1/2 x to the negative 1/2 times 1. When I multiply this by the x, what do I get? Because I have an x to the negative 1/2 and an x to the first, I have to add the powers, and that results as a positive 1/2. Hey, wait a minute, I have another x to the 1/2 right there. That means I have 1 1/2 of them. or 3/2. I'm going to stop there with my simplifying. Here's the other way to do it. The other way to do it is to take this and multiply it out. If I distribute here, I get x to the 1/2, and then I get x to the 3/2, because it's a 1 plus a 1/2. Now just take the derivative of the power rule, and I see 1/2 x to the negative 1/2 and 3/2 x to the 3/2 minus 1, 3/2 minus 2/2. Those match. So it's completely your call. Which way do you want to do this? Do you think one way is particularly easier than the other? Then you should do it that way. Whichever way you think is the easier one. Questions? In this case, I think multiplying out was easier, but that's me. Here's another example, a very similar example. Once again, you are in a position where I have item in parentheses 1, item in parentheses 2, multiplied together, that's a product. You have a choice. Multiply it out now, then do the derivative, or do the derivative with the product rule, then worry whether or not you want to multiply it out. If I just multiply it out here, what happens? When I do the last pieces, I'm going to get an e to the x times the square root of x, which is still going to need the product rule, isn't it? Because I can't combine the e with the power of x. So if I multiply it out, I'm going to have to do the product rule anyway. That seems like extra work. Let's be lazy and not do the extra work. Let's just do the product rule right here from the beginning. So if I'm going to do the product rule, derivative of the first, leave the second alone. Then leave the first alone. Oops, write down the correct thing. And do the derivative of the second. I haven't done either derivative yet, but I know where they go. This piece stayed the same, so this piece is derivative. What's the derivative of 2? Yay. What's the derivative of 3 e to the x? Well, the derivative of e to the x is, what happens when I have a number in front? If the number was alone, it would be a 0, but the number's multiplied, so
3.
it just stays there. I only get a 1 when it's an x. Remember, the derivative of c times f of x is c times f prime of x. So that number stays out in front. That takes care of this part. Now over here, what's the derivative of 1? Great. What's the derivative of the square root of x? Same deal as I did up in the previous example. I should swap that around. Square root of x is x to the 1/2. So the derivative is
1/2 times.
This is a rewrite, which is why I didn't put it in the derivative spot. I convert the root to a power, then I can use the power rule. I'm going to leave this just like this. Absolutely no reason for me to simplify this any further at this point in time. Questions? Jordan, you looked unhappy with that document.
I was gonna ask, this is the last part. I understand why it's someone had, like, why is that?
Because when the power rule comes around, ooh, I forgot to put a prime up there. When the power rule comes around, the derivative of x to the n is nx to the n minus 1. What's a half minus 1? But it's going since it's a half minus 1, I took away the bigger part, it's got to go to the negative side. Not an uncommon issue. So don't feel bad because I get a lot of people like, wait a minute, why did that change? But it didn't change, right? It went from positive to negative, but it didn't really change. I subtracted 1, I just got lucky with the symmetry. Jack.
So we leave it like this?
Yeah, I'm perfectly happy leaving it like this. You could, if you want to, put the negative on the bottom, make it a square root again, and you could do a lot of simplifying here. Is it worth it?
Is how it's multiplied in here.
I wouldn't. They'd end up in the same part. So I'd end up with 3e to the x plus 3e to the x root x, right? I just write them next to each other. They're being multiplied together. And then here, 2 times 1/2 is 1. So I get x to the minus 1/2. And then I get 3e to the x to the negative 1/2. Oh, I forgot the 1/2. Isn't that disgusting? So yeah, I can do it, but it really doesn't gain me anything, does it? So I think I like it better this way, but like is a really rigged term here because I think this sucks. But I picked it because I can see, hey, sometimes there's a benefit to multiplying out, like the previous problem. And sometimes, like in this problem, there really isn't a benefit to multiplying out. You have the option to do the algebra in whichever order you want. You will end up with the same final answer. It's just which way did you get there? Did you take the left branch or the right branch? Your call. A lot of functions that we deal with regularly involve products. One of the most common that I use almost all the time is the idea of a pendulum slowing down. You let go of a pendulum, what happens over time? Eventually it comes to a stop, yes? Because of air resistance and all that other stuff. You start a spring bouncing. I'll take a really easy spring. The shock absorber's on my car. I hit a bump. Boing, 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 boing. I'm bouncing down the road, right? I don't want to look like a lowrider on airbags bouncing for the next 7 miles. So I would hope that eventually I would slow down and that oscillation would dampen out. That oscillation is a trig function. It's either a sine or a cosine. That damping factor is an exponential. I have to multiply them together to get it to work. More on that in chapter 9. Questions? You'll also see it in the physics class. Where I just multiplying. I already know how to do this. So I'm going to cheat. Let's divide. Well, if I were to divide, I'd write 1 plus x squared over x cubed. Wait a second. F prime and G prime. What are they?
You want two X, three X.
So F prime over G prime is 2x over 3x squared, or 2 over 3x. I can cancel x on the top and the bottom. Yes? I would like you to graph f of x, and I would like you to graph that expression f prime over g prime. All right, I want you to graph f over g and f prime over g prime. Those. Please notice the parentheses I've put in on this second part. Since you're dividing by the whole 3x, you need that. Otherwise, the calculator is going to do 2/3 times x, and that's the graph of a straight line. Hang on a second. This is the original function. This is the derivative. I see a problem. I know from this picture alone, this is the wrong thing to be the derivative of this. Why do I know that? Let's turn off the derivative for a second. This is my original function. 1 plus x squared over x cubed. If I ask you for the slope of a tangent line anywhere on this graph, what value would it have? What can you tell me about all the tangent lines anywhere on this graph? The slopes are all negative. As I go from left to right, these are all going down. These are all going down. But when I look at this function, yeah, those are negative numbers. Uh-oh. That's wrong. That's not the right thing to be the derivative. That tells me this is wrong. That should have a negative derivative everywhere except 0, based on the picture. But this is positive when x is positive. That's the wrong derivative. All right. That's a problem I need to fix. Division can be turned into multiplication. How?
Keep, change, flip.
Keep the stuff on top. Change the thing on the bottom to flip it over by making the power negative. So if I want to do this, I can take this expression and I can rewrite it keep the top, change and flip the bottom. Well, now I can do the product rule. Or I could multiply it out, couldn't I? Because those are all powers of x. If I multiply this out, what do I get? What was this one? Perfect. And when I take the derivative of this, I get negative 3x to the negative 4 minus 1x to the negative 2. Jordan, you with me on this one with the negatives?
Yeah.
Please notice, negative powers go in the bottom, right? So this becomes minus 3 over x to the 4th, minus 1 over x squared, and x to the 4th and x squared are even powers. Those are always positive. We've got negative numbers in front of both of them. This is always negative. Yes, it worked. This makes more sense. At least in terms of the pictures lining up together. Now, I'm going to go a little bit crazy. This works perfectly because I could bring this up, flip the power and make it negative, and that worked perfectly. Ah, crap. I can really only bring that up, the x cubed out of the bottom, because it was simple. This denominator is compound. It's got more than one piece to it. So if I go to bring that up, the whole thing needs a power on it. Really, I would have to do this. And this power within power jazz, because there's an addition in there, I can't simplify that. This is stuck. There's a way around this. There are two different ways to approach the new rule for dividing. One is to say, trust me, I'll explain it Friday. The other is to go through and say, well, I need to figure out how to do insides and outsides. But that's exactly what I'm going to do on Friday. So let's do it the simple way. Say, trust me on this. If I have a division, I have a top piece and a bottom piece. I'm going to do kind of like a product, right? I'm going to say, oh, I'm going to do them one at a time. Derivative of the top, leave the bottom alone. Derivative of the bottom, leave the top alone. When I was multiplying, I was adding. But division is kind of the opposite idea. So instead of adding, I'll subtract. This is almost what I want. Problem is this negative 1 power. If I were to take a derivative of something to the negative 1 power, I would get a negative 2 power, wouldn't I? Negative 2 powers go on the bottom. I promise the where this comes from will make more sense on Friday. But for the moment, I'm going to say, trust me. Hang on a second. If this is the right thing, then it should work up here. Let's go back to my f over g of x being 1 plus x squared over x cubed. And let's use this new rule and see if it works. F over g prime. Okay, wait a minute. This is the top, t. This is the bottom, b, t prime, b prime. What's the derivative of 1 plus x squared? And the derivative of x cubed. Perfect. Now, derivative of the top times the bottom minus derivative of the bottom times the top all over the bottom squared. Now, I'm the first person to tell you that this does not look like the same thing we had before. This certainly does not look like this until we do the algebra. Multiply this out, what do you get? Minus. Multiply this out. Cube squared becomes the 6th power. Power of a power means multiply together. Okay, hang on a second. I got a 2x to the 4th minus 3x to the 4th, right? That's going to leave me minus one of them. I also have a minus 3x squared. Minus 3x squared minus 1 x to the 4th over x to the 6th. Here comes the magic part. Split it up. Minus 3x squared over x to the 6th. Minus x to the 4th over x to the 6th. What happens when you simplify that? And it's on the bottom, right? What happens when you simplify that? It worked, master, it worked. Excuse me, I need to do that properly. It worked, master, it worked. Go watch the Dracula movies. So, I now have a new method for doing quotients that doesn't require me to have a quotient that is rigged to be simple. So here is exactly where I might use such an idea. I'm looking for a tangent line. If I'm looking for a tangent line, I need the slope and I need a point. Well, they gave me a point, so I need the slope. How do I find the slope of a tangent line? should be a chorus ringing to the heavens. The slope of a tangent line comes from the derivative. So I need to take a derivative. Y prime. Oh, look, e to the x over 1 plus x squared. That's a compound denominator. I can't pull it up. It's an e on the top. I wouldn't be able to simplify it anyway. So, quotient rule. Derivative of the top. What's the derivative of e to the x? Derivative of the top times the bottom. Leave the bottom alone. Minus derivative of the bottom.
Do it.
Leave the top alone. Over 1 plus x squared squared. The bottom squared. Now I'm not going to simplify squat here, because I was given a point. I want the slope at that point. That's the x value I need to plug in. So I need to take this derivative and I need to plug in x equals 1. Y prime of 1. All I have to do is replace every x by a 1. E to the 1. 1 plus, what's 1 squared? Minus 2 times 1 e to the 1 over 1 plus 1 squared. The bottom is 4. 1 plus 1 is 2. 2 squared is 4. What's the top? That's e times 2, right? What's this? 2e minus 2e. Is 0. 0 over 4, but 0 over anything other than 0 is just 0. Wait a minute, what kind of line is this? It's a horizontal line. And I know the y value it goes through. It goes through this y value. It's got a slope of 0, right? So y equals 0x plus e over 2. It's a number, horizontal line. I now have a substantially larger set of base rules for derivatives. Page 189. The derivative of a constant, the power rule, exponentials, constant multiple, sum, difference, and my two new ones, product and quotient. Those two are not on the exam. Those are. I will be posting the homework keys and the review sheet key in about 3 minutes. I will see you all on Wednesday for the exam.